Okay, I'll get moving here in a minute. I'll wait for more people to stream in. It's only about 12 in right now. If folks have any kind of questions, I know I haven't seen everyone in quite a while. So if you have any questions, things have changed, let me know. Occurred to me that I didn't put the grades in for that last one. I should do that after class. Yeah. Let's get another minute here. So. There we go. Okay, crossed an acceptable threshold here. Okay, I will go ahead and get started. So this week's lecture sort of follows up from loops. So last week, or I guess it's technically the week before last, I introduced loops, which, as you have all seen, are powerful but kind of annoying to use. If you haven't done any kind of programming before, loops are sort of a giant pain. Lots of small things can go wrong. You have to be careful with things. You have to do annoying stuff like pre-allocation. And if you use them a lot, you might find suddenly some loop that you put together runs inexplicably very slow, things like that. They can be hard to troubleshoot and deal with. So I like to follow up the necessary lecture on loops with a lecture on please don't use loops and use other things instead, which is today's lecture. Okay. Before I get into this, I want to make a quick little aside here about sort of just the process of going about solving problems in programming. So before you can write effective code to do literally any task, it's really important to know exactly what you want that code to do, right? If you don't know what you want your code to do, you're just sort of stabbing in the dark, hoping maybe something will emerge that looks like what you want, which is a common practice. I find people coding, but often sort of causes them to spend large amounts of time not really accomplishing anything because they don't really know what they want in the first place. So before you get started with any sort of coding problem, you need to ask yourself, this can be pretty fast, what do you want? Do you want to do some operation that produces a single value? Maybe you just want the mean of a number. That's easy. You know you want a single number. Do you want a vector of things, a list of things? If you're working with data, you should ask yourself things like, do I want data that are one observation, that is one row per person? Or do you want something like person year observations? If you had 10 years of data, 10 rows per person. Do you want your observations to be a single year? Do you want to aggregate a whole bunch of data together so just one row is 1 year? These sorts of things are important because they'll tell you how you need to like sort of operate on your data to get what you want. Most programming problems can be reduced to having an unclear idea of your end goal or the beginning state you're in. Most of the time when people are struggling to get something, I realize quite quickly that they don't actually know what it is they want, or they don't actually know what it is that they have. If you don't have the necessary data to get where you want, nothing you do is ever going to get there. If you don't know what you want in the end, it's going to be really hard to get there because you're just sort of hoping to stumble into it. So if you know exactly what you have, the exact data structure you have, what the contents of the variables are, their values and things, and you also know what you want, the intermediate steps are usually obvious in some way, shape, or form. When in doubt, I say you should sketch the beginning state and the ended state or the end state of whatever it is you're working on. And I mean this like actually physically is what works for me. I will literally draw a picture of the example data that I think I have, the example of the end result that I want. And sometimes I've even gone so far as to cut out the pieces of paper and reassemble them in the other way to see how you can translate the thing on the left, the beginning, to the thing on the right. Okay. If you can figure out a mechanical, like sort of by hand way to translate the former thing into the latter, you'll probably be able to figure out code that can do the same thing. The worst case scenario is by actually literally moving the pieces from one spot to another spot. Okay. Okay. If translating your beginning thing to your end thing seems too complicated to do, what you need usually is more steps. Think about how you can take baby steps from that beginning thing to that end state little bit by little bit. How do you take a whole bunch of columns and turn them into more rows, then turn those more rows into something else? Things like that, right? Break it up into many steps. Okay, so with that said, we're going to kind of do some stuff with functions, and I'm going to return to that sort of idea about how to like solve problems in general near the end. Okay. The first thing I want to talk about is vectorization, which I talked about a little bit 2 weeks ago. So this should be an example from 2 weeks ago, but I didn't update the title. So if you remember when we tried to find the mean for each variable in the Swiss data set, right? I could have done it with a loop. I could do it with an apply statement or something, but the best solution is just to use a function like column means and then not even have to think about pre-allocation, writing a loop, or even writing an apply statement, okay? If I want the mean of every variable in the Swiss data set, I can say, give me the column means of Swiss, and it's going to spit out a vector with each column name and its mean value under it. Okay, it just does it for us, and we don't really have to think about it. This is a vectorized command that takes care of all the hard programming stuff for us. And when I say the hard programming stuff, it figures out how to calculate the mean, not on one column, but on many columns in a row, and to do it very, very quickly. Okay, so column means will run really fast, even on like 100,000 columns, right? It'll just work. Doing that with a loop will be very slow. Okay. So loops are really powerful, and they're applicable to basically any situation. And when I say any situation, I mean literally every situation you can encounter, and you can figure out a way to do it with a loop. In some programming languages, you just do everything with a loop. Every single thing you ever do is basically looped. Okay. R is not one of those languages. Technically speaking, it is under the hood. Every time you do any repetitive thing, there's a loop somewhere, but R likes to hide loops from you so you don't have to write them yourself. This is good behavior and is desirable, so you don't have to write them. Okay. The thing is with loops is, well, they're powerful. You can use them everywhere. They're usually, at least in R, slower and basically always require writing a lot more code than some vectorized command. Okay? And we want to avoid writing lots of code because it makes us make mistakes, and we don't like slow things. Being a little bit slow often doesn't matter. Computers are very powerful nowadays, but for big data sets, it can make a really big difference. It really sucks when you're doing some sort of like data manipulation and you figure out it takes like 3 or 4 hours to do something, and you just have to like let it run and come back to it. If you have an operation that's taking hours to run, it's probably inefficient code that can be sped up unless you're working with like billions of rows. Okay. If you are, you probably know what you're doing. Okay. So whenever possible, I say you should use existing vectorized commands to solve your problems. Things like column means, or basically every function in dplyr is vectorized. The whole reason for the tidyverse, for tidy data, and for things like dplyr is actually to make it easier for you to use canned functions on your data rather than having to come up with sort of purpose-built things for every problem you encounter. If you have your data into a nice tidy format, you can use the same commands to do basically everything you want. The real sort of complex things that people end up having to use loops and stuff for are for untidy data. Sometimes your data can't be made tidy, but that's pretty rare, rarer than most people think. Yeah, there's one in chat. I had a GVD model that took 2 weeks to run. Yeah, sometimes models take a really long time to run. I know a lot of people who do not just big data stuff, but things in like genomics and things like that, where your models just run forever, weeks even, you know, and they just go and go and go. But sometimes you can gain a lot of speed, like something you might run in R that takes you a week to run. If you go and write that in something faster, like you do it in C++ straight, it might take minutes to run. So if you're actually in situations where you're doing stuff that takes a really long time, that's a good reason to go learn a faster language, or at least components of it, to do your stuff much faster. Okay. So sometimes no function will exist to do the thing that you need. There is no vectorized function for it, so you're going to be tempted to do something like write a loop. Okay. And I would say if it occurs to you quickly and easily how to write a loop to solve your problem, and that this is something relatively fast, you're only going to do it once or twice, and it's working on small data, go ahead and write your loop. In basically every other conceivable situation, you should not write a loop. If your data are large, you're going to do it repeatedly or anything like that. You should probably instead do something like write your own function to do it, and then apply that function over your data if you have to do it repetitively. Okay. So that's what today is going to be about. Today's going to be about how do I write functions to do these things so I don't have to do a loop for literally every special problem I encounter. Okay, so let's get into writing functions. So some examples of existing functions in R are basically everything you've ever used in R to do an operation. It's all functions all the way down, right? One of the common ones we've used is mean. Mean is a function. It takes as an input some vector of numbers. Its output is a single number, which is the arithmetic mean of that particular input, right? dplyer's filter command is a function. Its input is a data frame first, the thing we usually pipe into filter as its first argument, and then a whole bunch of logical conditions. Its output is a data frame that has rows removed based on those conditions. Technically speaking, it's rows kept based on those, but same deal. Another function we've used is readers read underscore CSV. This is a function that takes as an input a file path on your computer, and optionally things like variable names or column types. And its output is a data frame that contains data read in from that file on your computer. Okay, so these are all functions you could conceivably write yourself in R, right? Somebody wrote these functions in R. We use them all the time, but they're functions like anything else. Okay, so why would you want to write your own functions when there's so many functions out there? Okay, well, functions can encapsulate actions for you. They can do things you might want to do many times. Here's some examples of things you might want to do repeatedly, or at least sort of consistently. You might want to do something like, given a particular vector, compute some special summary stats on it. Maybe you have a set of summary stats you always like to see for your numeric variables, and they aren't the summary stats by default put out by the summary function. You might write a function to do that. Another thing might be, maybe you have some vector like columns in a data frame, and you have some definition of what invalid or wrong values are in there. Maybe you're working with survey data and you know all the negative numbers are different types of missing values, and you just want to replace them with NAs. You might write a function to do that systematically instead of manually doing every single one of them in a case when or something like that. Another thing is maybe you have some particular way you like your plots to look. And instead of having to type out all of that ggplot syntax, you would rather just have a template you can throw things into, say, in reports. Okay, you could write a function that takes a couple arguments and then does all the rest of that stuff in the background for you. A last sort of thing was maybe you want to define a new logical operator. You've used things like the plus sign, the minus sign, %in. Maybe you want to make your own version of one of those that defines some sort of logical relationship. Okay, so these examples here, all four of them are things we're going to do today as an example of building out different functions. You might have similar things you want to do, and you can adapt the approaches we use today. Okay? This kind of gives you a nice tour of all the many different things you might use functions for. Okay. Some advanced things that I don't cover in this class but are common uses of functions. Often if you want to do parallel processing, that is, you want to make use of all of the computing resources on your multiprocessor or multi-core system, or you want to spread operations across multiple computers, you usually have to do a little bit of writing your own functions to make that happen. This is a really common application for people working with big data. Another common application is writing functions that make other functions. These are called function generators, and it's sort of a common thing done behind the scenes in the tidyverse. The way like the pipe function works, the pipe actually strings together a lot of function calls, makes them into one big function and runs that function. So behind the scenes, it's technically generating other functions. And lastly, this isn't exactly a functions itself, but you might want to make custom packages like an R package that contains all the functions you use routinely. I used to bundle all my functions together into one particular package, but now I have sort of project-specific ones that I've been doing this lately. Okay. But if you do happen to work in, like, let's say you work in a small lab research center, or you work with certain collaborators, if you constantly use the same functions across many projects, including things like ggplot templates, it can be nice to just distribute a package to the whole team and everyone can have everything be the same. Okay, so here's an example of a very simple function. So this is a function that will take some vector as an input, and it will output a named vector of the first and the last elements of its input. Okay, I'll explain how all the syntax works in a bit, but this is sort of just this is an example, then we'll make it abstract and we'll have more examples. Okay, this says we're going to write a function. We're going to write a function. So the function in R that makes functions is function. It's easy to remember. Function makes functions. We're going to name this function first and last. This assignment here looks like assigning any other object in R because a function is like any other object. Then we're just going to say inside this function, and notice the squiggly bracket here. What does this look like to us? This looks like our loop syntax from before, right? Our loops would say for something in this, blah, do a bunch of stuff in the brackets. So the brackets again say we're going to do a bunch of stuff in here all together at once. Question there, are function names case sensitive? Yes. Yeah, like everything else in R, it's always case sensitive. Okay, so this says here, inside this function, what we're going to do is we're going to say, we're going to create an object called first, assign to that x bracket 1. Well, where does x come from? The answer is x is whatever our input to the function is. So if I give something to this function first and last, it's just going to replace x everywhere inside of the function. We'll get lots of examples of this later. Then it's going to say the last object is x length of x. This is a way to subset the last element of a vector. And then it does this thing here, return, combine, first equals the first thing, last equals the last. Okay, we'll see how this works. So if I say first and last, the function I just generated, and I give it the vector 4, 3, 1, and 8, what it's going to do is you can imagine if you replace x up here in the body of the function with this vector c 4, 3, 1, 8, you could imagine, OK, c 4, 3, 1, 8 subset to its first element is going to get the number 4 and assign it to first. 4, 3, 1, 8 subset to the length of that vector. Well, the length of it is 4. So you can imagine this is replaced with 4. It's going to grab the last element of this and assign it to here. First here is the number 4. Last is the number 8. It assigns the number 4 to first, the number 8 to last, and it spits this out as the result of the function. The first thing is 4, the last thing is 8. So all the function did is substitute all of these x's inside of it with whatever I gave the function. Okay? We're going to see lots of examples of this. It's OK if it's still a little confusing. Okay. Thing is, though, is this function is kind of stupid. So if I give first and last a vector of length 1, well, what is it going to do? I say first and last 7, and it says the first element is 7 and the last element is 7. This is true. A length 1 thing, its first and last element are the same thing, but that might not be what we want it to do. What happens if we give it something of length 0? If I say, give me the first and last of numeric 0, which creates a length 0 numeric vector, which seems kind of nonsensical, but you can do that in R. You can make length 0 objects that contain nothing. Well, it can't get the first or the last element of it, so it spits out something weird. It says the first is NA and doesn't even give me a second thing. Okay, so this is like it breaking in sort of a way we didn't expect, maybe because we didn't think we'd ever give it a length 0 thing. So here's a question. If you save them, how do you make sure they're in R's library? Do you just start your own library? Is there a folder for functions that get loaded by default? So loading things by default is not always really a recommended thing to do in R, because if you give a script to somebody else, they won't have those things loaded. So it's highly recommended you don't do that. You technically can, in your R startup files, load whatever the hell you want. But I recommend not doing it. In fact, I recommend just sort of writing them bare. Rather, what you'd normally do is I would normally just have a source file. So if I want to run, let me see. If you have some sort of a, maybe you have a .r file that contains the functions you want, you might just have a script file. You can just say source my functions.r, and it will run that file, and it will put those functions in your global environment. This is sort of the primitive way of running the rough equivalent of a local library or package. It just runs the script and puts them in your environment, and you would put that at the beginning, basically, of your script. That's the simplest thing. A more complicated thing to do is to actually write the package in proper R package format, and then you can load it with library that way. Making R packages isn't particularly hard, but you got to jump through some hoops because they need a particular structure. If you're going to have other people using your functions, you most likely will want to do them as a package and distribute them on GitHub or something. So you define every custom function in the script in which you use them in. It can get cluttered. So what I usually do is I actually have a totally different script. So as an example, if I go over to this chapter of my dissertation that I was working on today, let's see, mediators. Yeah, so here's an example of it. Before I run these models I have, so these are structural equation models. Before I run these models, I have this thing up here that says source syntax project functions.r. So what this is doing is it's loading the functions. And the question is, what's project functions.r? Project functions.r contains all of the commonly used functions in this particular project I'm working on. So I have a custom standardized function, a not in function. I have some data checking functions, things for extracting empirical Bayes residuals, a special list missing function, getting hierarchical model reliability. I have all these functions that I use throughout my projects, but I just kind of go and load them that way. But by using this sort of source project functions at the top, this is kind of like doing a library call, but I'm too lazy to write a whole package for it. So I just do it that way. So it doesn't clutter up this main thing. Not that this isn't still cluttered with way too many models. So, yeah. Okay. So in this particular case, our function is pretty dumb, right? If we give it a length 0 thing, it just breaks. If we give it a length 1 thing, it just gives us the same thing repeated. So maybe we want to make this function a little bit smarter. So what we can do, for instance, is we might make it so that this function checks the inputs we give it before it runs the function, so it can spit out an error message if we give it something unexpected. So I'm going to run a function now. I'm going to write a function called smarter first and last. I'm going to assign to that, it's still a function of x, which means it takes 1 argument. And what is it going to do with x? Now what I'm doing is something a little bit different. This was the old body of the function I used before that got the first and last elements of x, but I've added something at the top using flow control we learned 2 weeks ago. I say here, if length of x, that is the length of the input to this function, if it is length 0, the thing has no length. So I'm going to say, stop what you are doing and say the input has no length. This is how every error message you've ever encountered in R was actually written in the function. It checks for some sort of condition, and if that condition is true or false, depending on what they want, it stops running the function and yells some red text at you in the console. This is where error messages come from, the birth of the error message. It's usually the stop function. Okay, so how does this work? Now, if I say run smarter first and last, I give it numeric 0, it now says error in smarter first and last numeric 0, the input has no length. Where did this come from? It literally just spit out exactly what I told it to do. If you encounter a length 0 input object, stop and report that. If, however, you give it something like the original numeric we gave it, it looks at this and says, well, the length of this is 4. This is not a length 0 thing, so just run the same function we had before and give me the first and the last of this. Okay? That's how you build error checking into a function. So is there a way to open or display the source code of a function you're using so you can see what it's doing? Absolutely. I actually have this on a slide in a minute, but I'll show you. Actually, yeah, it's actually the next slide. Okay. So if you type any function in R without its parentheses or arguments, it will show you the inside of that function. So if I write my smarter first and last and then say smarter first and last, it will just display the interior of that code. Another thing you can do is highlight your cursor over any function in your syntax file and hit F2 and it will open it up also. So I'll show you. Let me browse back to 508. Okay. Here's an example. If I just say the table function in R, whoop, no parentheses, this is the source code of R's table function. It's surprisingly complicated. It takes a lot of arguments. It does a lot of things. But that's it. That is the entire thing, right? So most things in R can be opened this way. Most R functions are written in R, so you can dig into them and see how they work. If I do something like dplyr filter, you might see something like this. Use method filter. This isn't very informative. This is a symptom of object-oriented programming. When you run the filter command, you're not actually running filter. You're running a function related to it that is specific to the type of data you give it. So instead, it's probably filter dot data frame. And then it's going to say something like this. Filter rows data dplyr row slice. And you're like, well, what the hell is dplyr row slice? It's this thing, which again is a use method on this. Sometimes browsing into the source of your functions doesn't give you anything immediately useful because they're very complicated and it's many functions nested all the way down. But most of the time, you'll get at least something when you look at it. Other times, you're going to see something like this. The mean function is use method mean here. Same thing. Well, if I do mean dot what? Mean dot default. That's how it calculates the mean. So sometimes you got to trace these things down if you want to know. But it's all there. R is an open book. Unlike many statistical software packages, everything in R, if you get used to sort of how to browse and find these things, you can crack down to the code basically all the way down, at least until you reach the underlying language this stuff is written in, like C++. Very often you'll get far enough down, you just run into a bunch of C++ code. You can't go any deeper. But most of the stuff in R is written in R, so you can see all of it and how it works. Okay. This is kind of nice. Sometimes you like load up a package you're working with and a function is broken because the package hasn't been maintained. You might actually just be able to modify that code and make it work again. This has happened to me a couple times. Okay, so that's how you crack open a function. So let's get into the abstract of a function now. I've given you sort of the example of building one, but it might not all make sense. So this is the anatomy of a function. So you've got the name of a function, which, like anything else, is just what you assign the function to. You make functions with the function. Functions take arguments here. In this example, I've got argument 1 and argument 2. Argument 2 has some sort of default that it will take. So you give defaults to an argument here after an equals. Functions then have a body, and they have some kind of a return where you specify the output you want it to spit out. Okay. So names are like names of anything else in R. This is just what you assign a function to so you can use it later. Something unusual about functions it's not really, if you think about it hard enough, is that you don't actually have to give a function a name. If you want to use it right away, you can do what's called an anonymous function. This is writing a function and not assigning it to a name and just running it. I'll show some examples of that later. We've actually been doing it all term without me calling it anonymous functions. Functions take arguments. The arguments are the input or the parameters to a function, depending on the lingo you want to use. These are just the things you give to the function that tell it how to work. Okay? Examples of this, like in the mean function or something, you might say it takes the arguments x and na.rm. So here I'm writing a function called my new function. I assign to it a function and I say it takes the arguments x and na.rm. And then you'll notice here I say na.rm equals false as an argument. If you give an argument some value to begin with in the function up here, this sets it as a default. If the user doesn't specify na.rm equals something, it will just be false inside of the function. This is actually the way like the mean function in R works. By default, it uses na.rm equals false, and it doesn't remove missing data. Meaning when you want to remove missing data from mean, you have to say na.rm equals true to override the default. If I go into a help file for a function, for instance, the mean, you'll see over here, it's that exact structure. It says it takes the mean of x, x being something you must give it. If a function doesn't have a default, you have to give it to the function. But mean also takes arguments like trim and na.rm equals false. I can override this with na.rm equals true, but by default, it doesn't drop missing data. Okay? That's how defaults work. Some functions have a lot of defaults. For example, the table function, I can give it one variable, but then notice it has all these additional arguments we don't normally give to it. These are defaults that you can change if you want. Sometimes functions go crazy with the number of defaults. Read.table has this many arguments it takes, and all of them except the first argument have defaults. Okay? So you can change a lot of stuff. But it means somebody explicitly had to create all these arguments and set defaults in them so that you don't have to set them manually. Just know that they're there, though, and this is how you can do that yourself. Okay. A thing about functions that separates them from loops, anything that you put into the function that's an argument, like here, argument 1, argument 2, these things will not exist outside of the function. If I run something in the function and it creates objects and stuff inside of it, these don't exist outside of the function. Once it runs, they're gone and they don't go into your global environment. Okay? So you can create as many objects as you want inside of a function, you run it, and nothing will appear in your global environment. Okay? That's all contained. This is very different from a loop, where anything created in a loop goes into your environment. Because loops, you're actually running the code line by line repetitively in here. Functions actually operate in something called a different environment, which I don't really get into in this class, but just know the things you create in the function don't appear in your global environment. So you can go wild. Okay. The body of a function contains all the actual operations that your function does. This can be whatever you want. There's a lot of things in the body of most functions. It can be anything. We're going to see a ton of examples in a minute. The return value here is how you specify what you want the function to output once it gets done running. This could be a vector, list, a data frame. It could even be another function. It could be nothing at all. Okay? If you don't specify a return value for a function, it still outputs something. It just outputs the very last thing the function calculated. This is usually what you actually want out of a function, so often you don't have to specify a return. I still recommend it to be explicit, but sometimes it's not the last thing you want. Sometimes you want your function to output something other than what it's run inside the body, but not always. Like sometimes you want a function that maybe generates plots or something or prints a bunch of stuff, but it outputs something like a message just telling you when it's done or something. You might be able to figure these things out on your own. Okay. Here's an example of a slightly more complicated function. So in this case, maybe what you want is to be able to run a function on some numeric data and get different summary information than the summary function gives you. In this case, maybe what we want is a report of all the different quantiles in a vector of numeric data. That is, we want something like this. I want to know what value represents the bottom 1%, the top 1%, the median, and then 5%, 10%, 25% in both directions, right? Big quantile report like this, maybe it's just a way for me to diagnose skew in my data, whatever. Maybe you have an advisor who just wants these sorts of quantiles for all the variables in a data set. Here you go. Yeah. So here'd be a starting point for a function like this. What I'm going to do is I'm just going to say, let's create a function called Quantile report. I'm going to name it Quantile report because it does reports of quantiles. It's going to be a function that takes two arguments. It takes some x here, which I'm just going to say is a numeric variable, any old x, and then it has a na.rm for removing missing data, but by default, it doesn't do it. Okay. How does this thing work? Inside the function, what it's going to do first is it's going to calculate some quantiles. It's going to do this using R's base quantile function. Quantile takes a numeric vector as an argument. It has its own na.rm argument, and then it takes some vector of probabilities that we want to chop up into the quantiles of our data. But notice I did something a little bit strange in here. I said we're going to call this quantile function. We're going to give it our input vector of data, but then I say na.rm equals na.rm. Anyone guess what this is doing?
Is it using the input that you feed it from the quantile report function?
Exactly. This is kind of interesting. What I've done is what I really want to do is to be able to give this function, quantile report, an na.rm argument, but the only place it's actually used is in this function inside of it. So what it does is it passes this false down into this location, but if I run the function with na.rm equals true, it passes the true down here. These can be the same names here and here. This thing is going to get replaced with whatever this top level argument is up here. This is an argument to the quantile function. This is a common way you'll see this done. If you need to pass one argument from your function into a lower level function inside of it, you can do something like this. Just pass it down. Okay. Then I'm setting fixed probabilities here. I'm saying no matter what this quantile report runs, I don't have an argument for the probabilities. So every time we run it, it's always going to give us these probabilities, which are the first percentile, the 5th, the 10th, the 25th, the 50th, the 75th, 90th, 95, and 99th percentile. Okay. So here's a good question in chat. Why are we using na.rm equals false instead of true? Because that is what I decided. I tend to believe that you shouldn't automatically remove missing values. You should be explicit about it. But you could, if you're in a particular project where it makes sense to have it be default to true because you're tired of typing na.rm equals true, you could just change this default to true, and then it would always default to dropping the missing data. It's totally up to you. This is one of the wonderful things about writing your own functions. You can set all these arguments. In fact, one of the most common uses of writing your own functions is just to take some existing function and change all of its defaults. So you might run the function exactly the same way, but you're really tired of constantly using the same arguments to it. Just change them all and make your new function. It's a really common thing to do. I do it all the time myself. Okay, I don't name it the same name as the old function. I write my own, but still I do that all the time. Okay. So it calculates these quantiles. The quantiles are just the representative value of that particular percentile. And then it's going to name them. So it creates the quantiles and then it assigns names to them, which I just manually assigned. These are the bottom 5, 1, 5, 10, whatever, then the top. And then I say all I want this function to do after that is return my quantiles. If I say take a random standard normal distribution, 10,000 observations, I run my quantile report function on it. This is what it reports out. So what it did is it cut this data up into these quantiles. It gives me the numbers of them, and it labels them to tell me what quantiles they are. The bottom 1%, 5%, up to the top 1%. If you're familiar with sort of the standard normal distribution, you'd know that these are the correct quantiles for these sorts of values. You would expect your bottom 5% to be about negative 1.64, your top 5% to be about positive 1.64. They should be symmetrical. They're a little unstable at the 1% ranges here because there's only 10,000 observations. But here's a nice quantile function. Okay. This is a relatively simple function, but it does a couple complicated things. If you want to do something similar to this, steal the code and modify it and see how it works. Don't necessarily have to start fresh. Questions about that? Okay. Hopping along. So I want to do a quick aside on apply functions. Apply functions will help you get a lot more power out of functions built into R and also the functions that you write yourself. And many of the common functions you use in R actually have these apply functions inside of them. Okay, so writing loops sucks. I've tried to say this many times and in many different ways, but loops suck. Everyone hates loops who works in R. They just suck. Try not to write them, okay? So they're challenging, they're hard to read, they're easy to make mistakes. You have to write a ton of code. When they break, sometimes it doesn't make any sense, okay? The nice thing in R, unlike many other languages, is it has a built-in system for skipping writing loops. These are called the apply functions. So loops are just not the only way to iterate. They're not even the best way to iterate in R. Apply functions work like loops. They iterate over all the elements of some object. The difference between apply functions and loops, though, is you don't have to do any of that pre-allocation. You can just directly assign their output to something and it allocates it for you. So you don't have to be like, well, I think I want a length 50 numeric vector, so I have to create an object with numeric 50 ahead of time to assign things to my loop into it. You don't have to do that. Apply will create that thing for you as it runs. The difference with apply functions, though, which seems like a weakness at first, but really isn't, is that apply functions must use a function. They can't just have a whole bunch of code stacked on them. You got to run a function inside of them. The thing is you can make any code in R into a function, so this isn't really a limitation. So basically, everything you could do with an explicit loop in R, that is writing a for loop or something, can be done way more easily using an apply function in R. Okay, I'm going to show you. So here's an example of taking the Quantile report function we just created and running it over a whole data frame. So the lapply function, which stands for list apply, will apply, that is, it'll take a function and run it over a list of any kind. It'll run it one time for each element of the list. Now, as I've been saying over and over in the term, and this is when it begins to become important, data frames are not matrices. They are lying to you, and they are a list, and they are a list where each element is a column in the data. This means if you run an lapply on a data frame, it'll run any function once on every column of the data. This makes lapply really damn powerful for working with data frames. So here I say, I want to apply my Quantile report function to the Swiss data set. So we say lapply, the thing I want to apply it to, the function I want to apply is Quantile report. What gets spit out is for the fertility variable, here's its quantiles. For the agriculture variable, here's its quantiles. For examination, here's its quantiles. And then I truncated my output, but trust me, it did it for every variable in the data set. Okay. This is way better than writing a loop. This is only slightly worse than something like the call means function. But in this case, we even wrote the function it's using. Okay, so if you can come up with a function to do what you want on one column, you can do it to every column. So you just lapply. Okay. So One bummer about lapply is that it spits out a list to deal with. We all hate working with lists. I've been working with lists for years and I still hate working with lists. So when possible, I try not to get a list as output. sapply stands for simplified apply. What it will do is it'll do the same thing lapply does, but it will grab the output and try to convert it into a matrix as an output if it can, or a vector. In this case, if I say sapply Swiss quantile report, the same thing I ran before, but with sapply, what we get out instead is this prior output that was a list stuck together into a matrix where each column is a variable, each row is an element of that original vector that we had. So what this essentially did is took our output from the previous thing and C-bound it together, did like a C-bind together into a matrix. Okay, so this takes that quantile report and makes it into a nice matrix of things we can deal with. Okay, so sapply simplifies your lapply output. It still only works over something that is a list. Vectors count as lists, though, so you can apply over a single vector too. Okay. Is this a good time to ask about tidy output from functions? I heard this is something tidyverse tries for us. This is a way to try to bake this into our functions. Yeah, actually. So essentially, it depends. If you want to make functions that like sit in the pipe chain as their own standalone functions, it's easy. Just make them take a data frame as their first argument and make them output a data frame, and it will fit into the pipe chain. If you want to make something produce tidy data, you basically just want to make sure it spits out a tibble, doesn't even necessarily have tibble, but a data frame, and doesn't fuck up the format. That's pretty like straightforward. Don't like suddenly make it wide data or something unless you mean. But basically, if it takes a data frame, it spits out a data frame, you're probably good. If output is identical but more tidy, is it ever better or mandatory to use lapply instead of sapply? It just depends what you want. lapply I commonly use if what I'm putting out can't be a data frame, which is pretty often. Like I usually use lapply with running models and stuff. It doesn't make any sense to spit out a data frame, so I just use lapply. And lists are easier to work with if each element is a model or something. Usually sapply does. I mean, if you're working with data frames and you want a data frame out, you probably want sapply. Or what you really probably want is to work with per package, which is the tidyverse apply package, and you can just use map. I don't teach it in this class because it adds one more layer of confusion to everyone. But if you really want to do sort of tidy apply type things, I would actually use the per package. I typically still use lapply because I'm old school, but map does the same thing. Okay. Yeah. So there is also, in addition to lapply and sapply, there is a general apply function which works over matrices or data frames. And you can tell apply the margin you want it to operate over. That is, you can say, I want it to operate over rows. You'd say margin equals 1, or I want it to operate over columns, margin equals 2. I can replicate my sapply output from the last slide by saying, apply to the Swiss data frame on margin 2, that is over its columns, quantile report. And this will spit out a quantile report of fertility, agriculture, examination, education, and Catholic. If I change margin to 1, it would do the quantile report across the rows. So instead, these columns would be the names of all the different Swiss cantons, that is the rows in the data set, and the quantile would be meaningless because quantiles of all the different variables don't make sense, but you could do it. So apply is really powerful for working on matrices and things like that when you want to go across either rows or columns. You can also give it margins higher than 2 if you're working with multidimensional arrays. Most of us will never do that, but you might do it if you're working for doing higher level statistical operations. Okay, apply is very powerful. Okay, so here is an example from week before last. If you remember, we loaded in some data files last week as sort of an example using a loop. This was a pain, right? I had to do something like this. I had to say, I want to create a list of files, which is list.files in the folder filled with the files. I constructed some paths by adding that path to the file list. I cleaned up the names for these files by saying, here's the file list, remove.csv from all their names. I pre-allocated a data list to store the data in by saying I want a vector of type list of equal in length to the number of files I have. I assigned some nice names to them, and then I said I will need to run a loop for I in sequence along file list. If there's 10 files, this is just 1 to 10. Let's assign to data list this particular named element, this particular CSV file obtained from this particular path, then bind them all together into one data frame and display it. Okay. This was a big, long process to load in a whole directory full of files to get a single data frame. This is the sort of thing I want you to do on your homework this week when you say loops. But in real life, you probably won't do it this way because it's a bit of a pain. We could instead do this with a glorious lapply statement instead. I could say instead, I want my complete data to be the result of lapply over all those file paths, the read CSV command. So this says, run the read CSV command, but pass to it one at a time each one of our file paths. So it's going to read CSV. If we have 10 files and file paths, it's going to run read CSV 10 times. This right here is going to output a list where each element is the result of read CSV on a given file path. I send this to bind rows, and it binds them all together into one data frame. I spit it out, and we get one nice tibble. So in what is essentially one line of code, really can replace pretty much all of this garbage. lapply makes your life a lot easier. I don't have to do any kind of pre-allocation, any of that. It can just run it all for us iteratively. The thing is, though, is there's an even faster and easier way to do this with a truly vectorized function. I've mentioned before, I don't remember if it was in lab or in lecture, the vroom package. I could load up library vroom and literally just say, vroom the entire directory of files, and it will automatically run through them all, iterate, read all the files, and spit them out as a data frame and do it in that one command. If you have a giant directory filled with CSV, TSV, or similar files like that, they all contain the same columns, and you need to put them together into one data frame, you have no reason to ever do anything other than this. Okay? Vroom will devour the entire directory, and Vroom runs much faster than every other way of reading CSV files in R. It's basically instantaneous. So you can do it this way. Don't do this in the homework. I want you to write either an lapply or a loop, but this is a good way to do CSV files. lapply is much more general, so I want you to get a little practice with it. Okay. So you can convert almost any loop you have ever written into an apply function using a relatively straightforward process. Okay. Whatever you iterate over in the loop. So when you write a loop like for I in sequence along X, just discard the I and the in and give whatever you're iterating over, like sequence along X, as the first input to lapply. This is what you're going to iterate over. The body of the loop, everything that was inside that loop, just put it inside of a function instead. Okay? This function should only take the iterator index as an input. Whatever was I before, it should now just be function of I, and otherwise the loop will be basically the same. And then assign the output to whatever you were going to store your loop values in, and it will generally just work. Here's an example. Let's say I have a simple loop here where I want to create some, basically what I'm going to do is I'm going to pre-allocate an empty vector of length 5. I say loop vec is an empty numeric vector of length 5. And all I want to do is I want to fill this thing up with the squares of their index. So this is basically saying sequence along loop vec This is a length 5 object, so this creates a vector 1, 2, 3, 4, 5. Okay. Inside the loop, it's just going to replace x with 1, 2, 3, 4, and 5 here and here, which means it's going to assign 1 squared to the first element, 2 squared to the second element, 3 squared to the third element, and so on. If I display this loop vec, I get 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared, right? This isn't doing anything fancy, but this is a loop to do something. Well, the thing is, this is how I could do it with an S-apply instead. I don't have to do any pre-allocation. Because I'm not doing any pre-allocation, I'm not even going to do sequence along loop vector. I'm just going to iterate over the numbers 1 through 5. I now put the body of my loop inside of a function. I just say, iterate over 1 to 5. What function are we going to run? We're not even going to name the function. I just say function of x is x squared. What this does is it passes the numbers 1, 2, 3, 4, and 5 to x, which puts them here, runs them all one after another, spits it out to this vector. I display it, and it's exactly the same results as the loop with half as much code, and it probably ran a lot faster. Okay? So you can convert loops like this to an apply function, and it's better in basically every way. So whenever possible, do it this way. So this is a great question in chat. Then under what conditions do we still need to use a loop? Okay, there are a very specific class of operations that basically always have to be done in a loop. And this is when every iteration depends on the previous iteration's result. Okay, so the thing with an apply function is it basically independently runs every one of its iterations on its own. So it runs the 1, 2, 3, 4, 5 of this. It basically runs them simultaneously, more or less, which means it doesn't go and check what it did on the prior iteration before it runs the next iteration. You can, however, make loops where the current iteration depends on the prior iteration. This is a really common operation in Bayesian statistics. So anytime you do Markov chain Monte Carlo, which is the backbone of basically all Bayesian statistics, each iteration depends on the value of the prior iteration, so you can't parallelize it. You must do them serially or sequentially. Because of this, every Bayesian statistics operation you ever see is a loop somewhere. Okay, and that's just the nature of the game. So things like that, you got to do it. If you want to do things like simulate a random walk, you basically have to do a loop usually. Yeah. So iterative things like this, generally it works. But Bayesian stats, this is actually the reason why Bayesian stats is so computationally intensive, because you can't actually parallelize it nicely. What you can do is you could break it up into chunks and parallelize them, but you still have to allow the Markov chains to go sequentially. R is very, 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 very slow at doing that sort of operation. So every Bayesian stats package in R doesn't actually use R to calculate those things. They're all written mostly in Stan or Bugs, other languages based on C++ that are much faster. So if you have to do those sorts of operations and you do them with a lot of data, I recommend doing what everyone else does, which is write them in a faster language for sequential operations, which is usually Fortran or C++. Okay. Few people realize that Fortran, the language, the highest language of the 60s and 70s, is still alive and well in statistics because it is very fast. Still used in things like climate modeling and stuff because it's so much faster and everything else. Anyway, so back to making and using functions. Okay, so an example of something you might want to do is maybe you want to discretize a bunch of continuous data. That is, you've got something continuous like income, and you want to create maybe ordinal categories for it. Okay, so you want to look at a distribution of data and then group them into some sort of buckets, maybe based on a distribution, maybe by evenly breaking them up. So something we do kind of commonly. Discretizing your data is usually a bad thing if it's going to go into statistical model, but it's really good for human readable information. You can't just provide people a table of like every income of everyone in your survey, but you could bring them a nice like sort of histogram or something of it. That's discretizing your data. Okay. So there's already a function in R that will break data up into buckets of things, that is, categorize it. The problem with this cut function is you got to tell it where you want to cut the data up, or you got to tell it how many buckets you want to break it up into. What I want to do here is I want to make what I call a convenience function. This convenience function will just sort of default to cutting up in a particular way, or allow me to give it quantiles instead and split it up into some sort of buckets. Okay, so this is something where I can be like, okay, I want to break my data into the bottom third, the middle third, and the last third of my data and spit out buckets. I don't have to go and look up where those are in my data and give it cut points, things like that, right? So what I'm going to do is I'm going to write a function called bucket. I'm going to assign to this a function which takes two arguments. It takes x, which in this case is just going to be some numeric vector, and then it takes a vector of quantiles. I'm saying here, by default, it's going to do the first third and the second third. So this is 33.3%, 66.6%, which I want to basically say, cut it at these two locations and give me three things as a result. That is below 0.33, in between these two, and higher than that. Okay, how's this going to work? So what I'm going to do is I'm going to set something. I'm going to say I want to set a low extreme for my data. That is the minimum value I want to include in a bucket. I want to set the quantile points I want to break it up into, and then some high value to capture every value in the data set. So basically, the low extreme should be lower than the lowest value in the data. The high extreme should be higher than the highest value in the data. Everything in between should be based on the quantiles I give my function. To do this, I'm just going to say, let's assign these new breaks in my data to this thing, new breaks. What's it going to be? It's going to be a vector of numbers. These numbers are the minimum of x minus 1. Well, the nice thing about the minimum of x minus 1 is, by definition, it will always be lower than every value I give it. No matter what x I give, it's a little bit lower. Okay, so this makes sure that the bottom end of my data, everything is always captured. I'm not cutting off something that I want to keep. Then I use the quantile function from earlier and say, take quantiles of our input vector x, break them up into quantiles based on whatever quantiles I give here. This just puts out the same thing our previous function did. Remember, it gave us numbers like 1.64. That's all that's going to do. It's going to give the values of the x vector at given quantiles. And then it's going to give a maximum up here that's one higher than whatever is the maximum value of x. This is a little bit abstract. It's okay if you don't exactly follow what it's doing, because it's going to become graphically apparent in the next slide. I then want this function to return the result of running the cut function on our x data, that is the input vector, with breaks equal to the breaks we just calculated right here. And I don't want to label the data. If you label the data, instead of returning like integer values for the bucket, it's going to give you a numeric range, which looks really weird. So just trust me, you don't want it. You could run this function and see what it does with labels true. It's probably not something someone would want. Okay. So this is what it does. If I say generate 100 standard normal distribution draws, I'm going to call them random data. I'm going to create now bucketed random data by running my bucket function on the random data. I say I want these quantiles. Let's divide it up into its 5th percentile, 25th, 50th, 75th, and 95th percentile. And then I do a quick plot of the data. So these are the actual values of the random data. Low values here, and see they're kind of increasing monotonically across. So these are the actual continuous values, right? So they go range from somewhere around below -3 to a little bit below +2. What my bucketing has done is it's converted every value below whatever quantile is here. This is the 5th percentile here. It's converted them into bucket 1. So all these low values on the continuous scale are now in bucket 1. The values that are a little bit higher but still essentially below the median are in bucket 2. This is bucket 3, bucket 4, bucket 5, bucket 6. So we've essentially converted continuous data on the y-axis to categorical ordinal data on the x-axis, right? So if you bucket something ordinally, right, you should never have any overlap, like any value here must always be higher than a value over here and so on and so forth. This is just a way to quickly calculate bucketed data if you want it for some reason. A common application of this, for instance, would be breaking up income into, maybe you want buckets based on quartiles of income. Okay. So was there an opportunity to name the buckets? Yeah, I absolutely could. I could take this function here where it says quants like this, and instead of just returning the cut up values, I could make it return labeled ones. So I might do something like assign labels to this cut up here by, say, creating an object and then setting its names. I absolutely could do that. You could just dress up the function that way. And that's sort of the thing. If you make a function like this you're going to use, you don't really have too many excuses not to make it do exactly what you want. You're only going to have to code it once no matter how many times you use it. So make it do all the things you want to do and make nice, pretty output. And then you just use that function and never manually type all that crap out again. Okay. Can you explain this part? C minimum, quantile x, max 1. Sure. Let me just copy that into R and show you what it's doing. Okay, so let's say I have, I'm just going to do R norm 50, example data. If I look at my example data, this is just 50 numeric values like this. Okay, if I take the data I had here and say, put example data where all the x's are, quant's not found. Oh, I got to provide some quantiles. See, let's do 0.33, 0.66. Okay. So what this is essentially doing is if I take my example data, let's arrange it so you can see it in order. So you'll see here that the minimum value of my example data was negative 2.55. Its maximum value was 2.9. What this is essentially saying is, I want to be able to create cuts in my data where I start with the minimum value here and then go one lower. This is just a way to make sure I'm getting the lowest values in my data no matter what. And thus the lowest value in my cut is negative 3.55. I then say I want quantiles of example data at the 33rd and 66th percentiles of my data, which happen to be negative 0.73 and positive 216, which gives me these two numbers here. And then I do the same thing with the maximum I did with the minimum. 3.94 is just this plus 1. Now, if I divide my data up such that I take all the values between this number and this number, I put them in one bucket. Bucket number 1. I take all the values between these values, put them in bucket 2, all the numbers between these values, and put them in bucket 3. That's what the function is doing. Does that make sense?
Yeah, that makes sense. I guess my question is why we need the minimum minus 1 and the maximum add 1 instead of minimum and maximum directly.
Okay, so let's see what happens. Cut example data probs equals, let's see. So, label equals false. Okay, so I get data that looks like that. So I'm going to take test probs, not really probabilities, but we'll call them that. Okay, so you'll notice some things have changed between these two here. What's actually happened is by default, the way cut works is it expects that the values must be between the values provided. And the minimum values are not between, for instance, the minimum and the next highest. They are equal to the bottom one. As a result, the low values, the values that are equal to the minimum, are going to end up as NAs where I don't have a floor that's below them. This is to some degree stupid behavior. It's non-inclusive subsetting, basically, but that's just the way it works. I don't think there's an option in cut to say inclusive. There is, in fact. Should be closed to the right or open to the left, vice versa. It looks like I could probably instead say cut equals false. No, that just reversed it and made it go the other direction. Nope, that solved nothing. Yeah, basically you just got to make them fully inclusive by adding or subtracting a little bit to get those minimums and maximums. Yeah. It's been so many years since somebody asked me why I did that. I had to look it up and check. It's just one of those things that's ingrained in me. You must use the function that way. And I was like, I have no idea. Let's look. Okay. Yeah. Okay. So here's another example. Let's say that we have data where impossible values occur. Okay. Let's say we have something like some data on a bunch of schools. In this case, I've got 10 different schools. I'm just creating fake data. And the variables are the percent passing some standardized exam and the percent who are of students on free lunch. Okay. Free or subsidized lunch, which is a common indicator of like an area's like poverty rate, right? So in this case, in this data set, these are both percentages. So something we know about in our proportions, not percentages, something we know about proportions is a proportion should have a minimum of 0 and a maximum of 1. If you encounter proportional data that has things like -1, 99, -13, these are probably indicators either that the person inputting the data was mildly incompetent or they are missing values of some kind, right? Okay, so we might want to write some sort of a function that we can give it a vector like this and a set of values to exclude and have it trim these values out. That's what we're going to do. So the goal here, right, is to write some function that will remove extreme or incorrect values. So what it's going to do is it's going to take as an input some vector of x, some numeric vector. It's going to have a cutoff for low values and a cutoff for high values. Anything below the low should be removed. Anything above the high should be removed. It's then going to output a vector where it has replaced the low and high values with NAs. Thus, it just replaces the extremes. It's going to filter out the missing or erroneous values. Here's an example of a function to do that. I'm going to call this function remove extremes. I'm going to assign to it a function which takes 3 arguments. It takes x, in this case, a numeric vector. It takes a low value, and it takes a high value. What is this function going to do? The first thing it's going to do is it's going to create something called x no low. That's going to be x with the low values cut out. I assign to that an if-else statement, which is a test if x is below the low value, return an NA. If x is not below our low value, return x, right? So this is just going to say anytime you get a value below that low, give me a missing, otherwise give me the original value of x. Okay. Then I'm going to create another one called x no low, no high, which is going to be x with both the lows and the highs removed. For this, I say, if else x no low, the thing we created up here, is greater than our high value, return an NA, otherwise return an x. It assigns that to this and then returns x with the highs and lows removed. Does anybody see something odd I did here? Something that doesn't make sense? I'm slightly abusing the behavior of if-else here. So you notice what I'm doing in this if-else statement? I say if x no low is greater than high, I'm not saying return x no low. I'm saying return x. But didn't x have those low values we didn't want and we're just excluding the highs over here? Do you know why this works to exclude both the lows and the highs here? Do I know why?
Because if else works step by step.
Not exactly. What else is happening here is that x no low has NAs where the low values were. And if you run a logical test on an NA, it returns an NA. And so it fails and returns an NA and still excludes the lows here. Okay. I could have instead put x no low over here and it would have accomplished the job, but I don't have to. This returns an NA where their lows have already been removed. So this is confusing, but it was a way for me to make it so all this fit on one line instead of extend slightly over the right side. Okay. Anyway, confusing, it's okay. So here's an example of running that function. I say here, I want to remove the extremes on school data proportion passing exam. And I tell it there should be no values below 0 and no values above 1. So it takes that vector, and anywhere it encountered a value below 0 or above 1, it replaced it with an NA, and it left everything else the same. So this is the type of little filtering function you could put in if you're working with a survey data set that has like, negative 90 through 99 as different classes of missings and things like that. You could just say there should be no values in this particular range, higher or lower, and it could cut them all out, and you don't have to do it manually for every variable or something like that. Okay. So speaking of not having to do it manually for every variable, the dplyr package has a function I've shown before called across that allows us to use a function on every variable in some set of variables at once instead of having to do it one by one. So what I say here is, let's take my school data and then mutate some new variables. In this case, I'm changing the variables. I'm going to mutate across certain variables. The variables I'm mutating across are everything except school. This is like select syntax. By saying minus school, it's going to run this command on every other variable in the data set. There's only 3 variables in the data set, so it's doing the same thing as running it on proportion passing exam and proportion free lunch. What am I going to do? So if we remember, across uses this funny syntax in dplyr where I say tilde and then I give it some function on the right. So I say what I'm going to do is I'm going to apply across these variables, that is everything but school, the function remove extremes, where I want to pass the variables to the first argument. I say x equals period to say pass all the selected variables here. I want my low value to be 0, my high value to be 1. This then runs the remove extremes function on both columns, removing all values below 0 and all values above 1. Okay? So if I had a lot of columns in my data set I want to do it to, it would still be this easy. I could just say apply it to all of them. So here's a great question. I think I've asked this before to get an answer. Oh, no, sorry. Is this mutate at or mutate across? It is indeed old and new versions. This used to be mutate at, but there is now this across function. It does basically the same things as mutate at and mutate if, but it can do all those things with one function. And it can do a few things that mutate at and if could not do. For instance, doing them simultaneously and things. So I teach across only now because they're kind of replaced those. Next thing, I think I've asked this before and I think you had an answer. Do you have a good general way to read or understand tilde? Yes, tilde means formula. And because it's a formula, you're essentially saying these variables, the output or whatever, are going to be something that depends on the stuff on the right. So you're essentially saying this is basically the same thing as being like y depends on x on the right side for a formula. Here it's a right-sided only formula, saying something that is going to be produced depends on the stuff to the right side of the tilde. In this case, the thing that depends on the right side doesn't have to be named because it's these variables and we're just going to replace them. If you want to create new variables, you could actually put names on the left side of it basically and say these things depend on the thing on the right. It's funky syntax. It's something referred to as a lambda function in general programming. Most people don't call it that in R, but it's their syntax that they use. It ends up being, it's actually from the package per is where it originated in R. It's very, very powerful. because it lets you do things like specify multiple arguments on the right side. You could even pass the variables to multiple locations using that, but it's kind of complicated. What the tilde here is really saying is it's saying don't treat this as a function over here. Instead, it's parsing it as text and behind the scenes convert it into a function call. Very complicated. You don't want to know about that, but that's what it's doing. Okay. So I want to talk just for a second about standard and non-standard evaluation, which I've mentioned a couple times in this class. Whenever somebody asks me, why does this function take unquoted names and this one takes quoted names? The reason is this ugly thing called standard and non-standard evaluation. So dplyr uses what in the grand world of programming is called non-standard evaluation. This means you can refer to variables without quotes around them. You can just write school if you want to refer to the school variable. Okay, programmers from every other language think this is an abomination and they think it's a terrible thing and they hate the tidyverse because it does it. But they're programmers who already know how to write code. It's very intuitive to the rest of us, but for them, they're just like, it's terrible. I don't use the tidyverse. I'm like, well, fine, go use data table. Be you, okay? Anyway, non-standard evaluation means we don't got to quote variable names, okay? The verbs in dplyr, verbs are things like mutate and summarize. They recently started allowing you to do things either way, which is very confusing to everyone, but also very powerful. So you can do some fun things. So for instance, I can say, take the Swiss data set and select quoted fertility in Catholic instead of unquoted, and no matter what I do, I get the same result. This is confusing because in the rest of the R world, things must be quoted or must be unquoted or they don't work, okay? You can do it both ways. The thing is, being able to do it either quoted or unquoted makes programming with dplyr a lot easier. That is, writing functions with it, because it's really easy when you write a function to pass text like this. It's really hard to pass an unquoted variable name in R. It requires all sorts of weird stuff I don't want to teach you and you don't want to know, but it's really easy to pass quoted text. So the fact it can do this makes your lives a lot easier. And hopefully you don't even notice how much easier it's made your lives because you won't know about the hard way we all used to have to do it. I'm going to see some examples in a bit. Okay. So another thing I want to talk about are anonymous functions. So you can skip naming functions in dplyr if you're not going to use the function again. The code below here, for instance, is something called an anonymous function. Here, what I'm saying is, for instance, I'm going to take the entire Swiss data set, summarize it across every column in the data set. This is how you used to do mutate all or summarize all. Now you just say summarize across everything. I want to run this function. The function I want to run is take the mean of the column, discarding missing values, and divide it by the standard deviation of the column, discarding missing values. Okay, this is an anonymous function. This over here is a function. It's two calls here where I've taken the mean, I've divided them by the standard deviation, but I didn't name the function and I didn't even use the function to define it, okay? This is actually what the tilde operator is doing. The tilde operator is basically doing the same thing the function in R does. It's defining a new function on its right side that takes something as its arguments, period is saying where to send those arguments, okay? Complicated and weird, but this is an anonymous function. Okay, it's anonymous because it has no name. If you want to run an anonymous function like this in lapply, sapply, or apply, you actually have to specify that it's a function first. You got to do it like this. If I want to run that function on the Swiss data set, I'd say lapply Swiss, specify I'm creating a function of x, then I say mean of x and SD of x, and it does the exact same thing the dplyr one did. So if you compare this to the dplyr one, you'll see the only real difference is instead of writing function of x, I wrote tilde, and instead of writing x, I wrote periods. It's the same syntax otherwise. They just like this one because the tilde is a little bit less annoying to write than function of x. Okay. If you need to pass multiple arguments, you can actually pass .x and .y. And if you need more than that, you can pass .1, .2, and .3. Anyway, gets complicated. Okay. So anyway, I'm going to get to the last extended example of using functions, which is using ggplot templates. Okay. So let's say you got a particular way you like your charts and you want to make lots of them like this, or you want to make it so you can quickly change them. So what I have here is I have a ggplot of the Gapminder data from week 2, which is then filtered down to Afghanistan. I am plotting the year on the x-axis, and then population in millions on the y-axis by taking pop dividing by a million. I'm making a line graph of it in a particular color. No X label. My Y label is population in millions. The title is population of Afghanistan since 1952. I give it a minimal theme, and I adjust the plot title slightly. Okay, so if I have a function that looks like this, how could I make this, not a function, but if I have something like this, how could I make a function that was flexible for any country? So instead of saying this must be Afghanistan, I could make it work for every country and update the plot accordingly. What needs to change here? Yeah, first thing, country equals this. And, right, there's a bunch of things, right? So first we need to make it so instead of country equals Afghanistan, we would instead say something like country equals X or Y. We would put it in the function and it would pass that thing to it. Okay. What else needs to change? That title, right? This is a sneakier and harder thing, right? How do we make it say population of the correct country since 1952? We're going to have to build that into this so that it can change. The next question, how would I make this flexible for any Gapminder variable? And I mean this on the y-axis, not just population, but life expectancy and all that other stuff. What would I have to change? Similar stuff, right? What's got to change? So again, the title does have to change because we have population of, but now the Y label has to change, right? So we're going to have something what this changes and this changes and this changes, right? We actually don't want this to just be any variable divided by a million. We want this to be like a variable here, and we're probably going to have to divide population by a million ahead of time if we want, okay? So if we want to make this flexible so that we want to write a function that just takes a country and a variable, we got to have a lot of different moving parts. So let's go ahead and do it. So we want our plots to look something like this. We want the plot to be like population of Afghanistan since 1952, population in millions. But we want to make it so that we can do things like this. We can make the same plot, the same function call, do life expectancy in Peru since 1952 and change the Y label to life expectancy. You'll see it's the same plot, but it's a different country and a different variable. And we want one function that can produce either of these plots with minimal effort. That is, we want some kind of template. See how we do that. So the first thing we need is we want to make it so this is a function that the user can input a string for country as an argument to the function to subset the data and get the title right. So the way we do it here, we say, let's create a function called Gapminder life plot. It's still only going to work for, in this case, life expectancy, but we're going to make country flexible. Because country is the only thing that needs to be flexible, this is a function which just takes one argument. It takes the country, okay? Inside this function, what we're going to do is we're going to say we're going to make a ggplot. We're going to take the Gapminder data and then filter it down so country is equal to our input country. If I pass Peru to this, it just sets Peru to here and filters our data down. Because we are doing always year on the x-axis and y is life expectancy, these are fixed and we don't have to mess with them. The geom line doesn't have to be changed. The X label doesn't have to be changed. Y label is just life expectancy. The theme doesn't change. What does change, though, is the title. We say here now, GG title, we have to paste together a title. We must assemble it from its parts. I say here, we're going to paste together life expectancy in a particular country since 1952. And so no matter what country I give it, it will replace this with the appropriate country and spit out the right title. Okay? Does this make sense here? Do I have an example? Yes. So for example, if I say Gapminder life plot country equals Turkey, it's adjusted the overall title to be life expectancy in Turkey, and I assure you this is the data from Turkey. Why do I have to write the function as country rather than country? I don't. I just wanted to make it easier to tell the difference between this and this, but I don't have to. I could have made this X, and I have to put X here. Yeah, I could do anything I want. So that just works. We now have a template, right? Here's a question. Why did I use null for X label? If you give null as a label, it removes that label. It's a quick way to delete the X label. You could also give blank quotes, like just 2 quotes with nothing in them, but null works here too. Okay. So as you see, there's no X label there. That's all that's doing. So we have a nice kind of simple plot. The next thing, though, is we have to do something substantially more complicated. We need to make it so the Y variable is flexible too. So we need to make it so the user of this function can specify a variable to put on the Y-axis and then fix the axes and the title, right? So to do this, I'm going to use a named lookup table inside of the function. I'll show how that works in a second. So here's a question. Why do you have to write the equals here and not just country in here? I actually don't. This was just an example of specifying it. If I delete country equals here, it'll work exactly the same because the function only takes 1 argument. So it works the same either way, but sometimes I just want to show the argument. It's just arbitrary. If it took 2 arguments, I might actually need it. Okay, so to make this thing able to look up and get the appropriate labels in my Y-axis and everything, I need to do something a little bit complicated. The reason for this is the labels that I want, for instance, on my Y-axis and my title are not just the variable names in the data. I actually need to dress them up a little bit. So the variable in the data, for instance, is life exp, but I want the label on the Y-axis to be life expectancy. The variable is population, but I want it to say population in millions. And GDP per cap is the variable, but I want it to say on the Y-axis label, GDP per capita in US dollars, right? Similarly, in the title text, when it's life exp, I want it to say life expectancy in. When it's population, I want it to say population of. And when it's GDP per capita, I want it to say GDP per capita in. Okay, so I'm going to use the actual variable names in the data, but what I want to assign are these values over here in the right. So what I do is I create some named vectors. I create vectors Y-axis label and title text. This is the way they work. If I create Y-axis label and I say Y-axis label and I subset it to the variable name pop, what comes out is population in millions. This gives me a way to use the input variable name to get the actual Y-axis text I want. It's a quick way to do some subsetting using named vectors to get something out. If you ever hear somebody say lookup table, that's all this is. The lookup table, you can use like dictionaries in Python the same way. Okay. Similarly, if I say title text and subset it to pop, what pops out is population of. So you'll notice I can subset the Y-axis label and title text using the same variable name, but get different text out because they contain different text. This means if I have the user provide pop as an argument for the variable, I can use it to select the correct variable and the correct y-axis label and the correct title text using just pop in quotes. This is very powerful, and we'll see it in the function in a second. Okay. The thing is, to use that inside of my function, I'm going to have to put these lookup tables inside of the function. Okay. So one side note about this, as I mentioned about standard and non-standard evaluation, ggplot is usually looking for non-standard evaluation that is naked variable names. If you give ggplot a quoted variable name, it will not work. If you want to give a quoted variable name to ggplot, instead of AES, you have to use AES underscore string. It's just something you got to do if you're programming with ggplot. It's a thing to remember. Here's an example. So our complete gapminder plot function is going to look like this. I'm going to assign to gapminder plot a function which takes just two arguments, the country we want to plot and the y variable we want to plot in that country. Then I have that lookup table I showed you before. I have life exp equals life expectancy, pop equals population in millions, and so on. The thing is, though, is I'm immediately subsetting this vector. What's going to be assigned to y-axis label? If you imagine we pass to this function GDP per capita as the y variable, it's going to look at this whole vector here, and it's going to subset it immediately to the thing named GDP per capita, thus assigning the text GDP per capita USD to y-axis label. Similarly, it's going to go down here, and to title text, it's going to find GDP per capita and assign GDP per capita in to title text. So I'm just immediately using this lookup table to assign some values. Thus, I can assign my y-axis to label to this, my title to this. Okay. The next thing I do here is I say ggplot, take my gapminder data, and then filter so that country is equal to country, the thing we did in the first version of this function. And I take one extra step. I say, and let's go ahead and mutate population to be population divided by 1,000,000, because we're expecting population in millions. Okay, I just do that inside here. Then I do this weird thing I said I had to do. We're going to say we want the aesthetics in here to be AES string. X is going to be the year variable, but because it's AES string, I got to quote year. It's just the thing we're going to do. The reason for that is because what I'm passing to y equals y variable, up here is the quoted variable name, like pop, life expectancy, or GDP per capita, instead of the unquoted variable name. AES string just lets me pass these text in instead of the raw variable names. I draw a line, I leave that alone. But now look how much flexibility is in our title. GG title is going to be paste together the title text, the country, and then since 1952, because we haven't made it flexible for year. So how does this work? Let's say we gave this function Peru and GDP per capita. What it's going to do first is it's going to look title text. Let's get GDP per capita, so it's going to write as a title, GDP per capita in, country is going to be replaced with Peru, and then since 1952. Okay, so it populates the whole title to say GDP per capita in Peru since 1952. Then null X label. The Y label is entirely defined by the text we generated here, so it's going to be GDP per capita USD if that's the variable we picked. Everything else stays the same. So for this, we've had to write a lot of stuff inside the function. So this is an example of doing a lot of work up front to save us a lot of labor later. Because now I can say things like this. Gapminder plot, country is Turkey, Y variable is population, and it just says population of Turkey since 1952, population in millions. Okay? So now we have a template thing. I can give it any country in the gapminder data, any variable as a y-axis variable. Okay, so why did you move to a string when you had a variable named year and the y variable is not also a string? What's the motivation for the change? This is a string. So the thing is y variable as an input to our function is always going to be quoted text, like pop. Yeah. So actually it is a string. It just doesn't look like it. The next one, can you use the replacement table y-axis label x outside a function? Yeah, I absolutely could use it outside of a function. You just have to make sure you're subsetting it right and everything. But the lookup table, it was convenient to put inside of it. Next, if your data set has many variables, can you create a lookup table with names my data xy, so only have to write the labels instead of rewriting all the variable names? Yeah, absolutely. Yeah, lookup tables are handy for all sorts of stuff. I actually like using reverso lookup tables where I have the name stuck to really long descriptive labels, and then I can search the labels for what I want and have it spit out the variable name I want. That's actually something we're going to see for tidy census in week 9, because it has the census full labels on the variables and you can search through them. So what's the syntax thought process you'd recommend for that? I'd probably use a data frame for it. I'd have one data frame that's the variable names and the next one that's like the labels. And then what I essentially do is I would subset on the appropriate one and spit the other one out. Yeah. Okay. So templates. You're going to do a template like this for your homework. The second part of your homework that'll be due the week after next. You'll make a ggplot template. Okay. One last example I want to give is making an operator. I just added this like on Tuesday because I was like, hey, why not? Let's do something weird. Okay. So if we remember, the %in function is a logical operator that returns a true wherever the elements on its left are equal to any one of the elements on its right. So if I have a vector like USCA here that contains Canada and United States, and I say take the gapminder data and then filter so that country is in USCA, right? It gives me the countries Canada and the United States. So it checks to see if the value of country is either one of the things in US and CA. Okay. What if you want the opposite of that, right? What if what I want is all the countries not Canada or United States? We can do it slightly awkwardly like this. I could just take the statement I did before and put an exclamation point in front of it, and it will reverse it, right? And so this would give me all the countries not US or Canada, the first two of which are Afghanistan and Albania, right? But I find this awkward because I see %in over here and I find it easy to miss the exclamation point over here. I would rather have an operator that does itself in the inversion of this operation. In fact, if you remember carefully when I showed the functions from that dissertation chapter a bit ago, the function I'm about to show you is in those functions because I use it constantly. So what we're going to do is we're going to make a %not-in function. We're going to make our own logical operator that does the opposite of %in. So what we can do is we can invert or negate %in to make a new not-in operator. This involves some wonky syntax we haven't really seen too much in R, but I wanted to show you how to do it in case you ever need to do it yourself. You can define a new operator like this. You want to put it with 2 percentages around it, kind of like the pipe in dplyr, and then whatever text you want inside, but you need to put backticks around it before assigning to it. So I'm saying backtick %not-in backtick. I'm going to assign to this the negation of %in. What the heck is this? This is a very lesser known R function. This is a logical negation of a function. This is the function version of exclamation point. The exclamation point inverts actual trues and falses. Negate inverts an entire function. So what this does is it takes the %in operator and literally makes it return falses when it should return trues and trues when it should return falses. It's not flipping the trues and falses, it's making the function operate in reverse. Kind of weird. Don't worry about how it works. So I create this like that. And now, happily, I can say, take my gapminder data and then filter so that country is not in US and Canada. And then I get Afghanistan and Albania. I've inverted an operator. This is nice for logical operators, and you can do it with every logical operator. anything that returns a true and a false as a function can be negated, which also means you can do weird things like maybe what you want is a function that it doesn't get numeric variables, it gets all non-numeric variables. I could say, let's make a function called isn't numeric, assign to that the negation of is numeric, and boom, what this will do is return a true anytime it is not a numeric variable. That is pretty handy, actually. So just know you can do it. Super R secrets. Okay. So any questions so far? I'm just going to kind of wrap up. No, if you want to make a new operator, it absolutely does not need to be a derivative of an existing one like that. I could put, I wouldn't use negate then. I would just assign to it an actual function. But you kind of have to specify it in a weird way. I forgot what the actual syntax you have to use is to specify it as an operator. I'm trying to remember if it just takes the first argument on the left and the second argument on the right. I think that's how it works. So you just say like function x, y, the left thing is going to be x, the right thing is going to be y. I could actually verify that. Let's see. Forgot how to get the source of the pipe. Let's see. Yeah, you can't peek inside the pipe very easily. So what I need to do is... That's funny. There it is. Okay. So for instance, here's how the pipe is. Yeah, left-hand side, right-hand side. So if you want to specify an operator, you do it like that. First argument's on the left, second argument's on the right. And if you're curious, this is the pipe function. This is what it looks like on the inside. It's weird, and there's a lot of crazy stuff going on inside of here. If you think about it, really crazy stuff. But anyway, that's how it works. Weird shit. The percentages, are they mandatory? I actually don't remember. I think it's generally yes. Basically, I think it has to be certain reserved things that'll do it. Like, so for instance, if I type like, okay, yeah, so it is the percentages are sort of necessary to specify it as an operator. There are certain operators, of course, which do not have percentage signs like plus and minus, but they're special reserved things. You can't assign something to plus and minus very easily. But you could look into it. I wouldn't be surprised if there's ways to do it without the percentages. No. Okay. Yeah, so anyway, to wrap up. So if something in your function isn't working the way you'd hoped, dplyr has built-in, not dplyr, but R has built-in debugging functions, which will sort of show you the world as it's happening inside the function. So if you did something like took our gapminder plot and you run the function debug gapminder plot and then run the function, it will run every line of code inside that function step by step. So if you don't know where your function is breaking, you can debug it and run it and go until it breaks something. If you do that, once you fixed it, make sure to turn debug off by saying undebug the function. Otherwise, it's always going to step through it piece by piece. You'll rarely need to use this, but it's good to know it's there. So the last thing, overview of sort of the process of handling programming problems. So processing data of any kind, doing any sort of like function writings and stuff is really complicated, and there's usually a million different ways to accomplish it. I believe that the general process that you should follow when doing it is something like this. So this is just sort of my general sky level advice. First thing, look carefully at the starting data you have to figure out what you can get from them. You'll be wasting all your effort if you can't get what you want out of the data to begin with. There's no reason to just try and squeeze blood from a stone. If you've got survey data but doesn't actually capture the thing that you want, just abandon it. Don't try and force something out of it when it doesn't exist. Next, if you can get the thing that you want, determine precisely what you want that end product to look like. If you know, for instance, the data frame you want to look like, you're like, I want one row per person with a respondent ID, these columns describing the person, that's the data frame I want. figure that out before you start trying to get there. Next, identify the steps you need to go from your starting data to your end product. Okay? You might be able to do it in one step. It might take lots of steps. Make every discrete one of those steps, every step to go from 1 to 2, its own set of functions or function calls. If at any location in this, a step is too confusing for you to understand by looking at it, or too complicated, it has a lot of code, break it into more steps. More steps are your friend. Don't do more things in one step than you are comfortable doing, because that's how you make mistakes. As you get more experience in programming, your steps will do more and more stuff in a single step. Okay, then, this is important, complete each step separately and in order. Do not move on to a next step until the prior step is doing exactly what you need it to do for the next one. And then don't worry about combining any of these steps for efficiency until everything works, and preferably until you have some good reason to make it more efficient. Long code that works quickly and does exactly what you want is okay if it works perfectly. You don't usually need to sort of optimize unless there's a good reason. If you got 500 lines of code to do a simple operation, by all means, reduce that so you aren't making mistakes. Okay, once you are finished, if you need to do all this again, convert those steps into functions so that you just call on the functions and it works, okay? But do this sort of process, it will make your life a lot easier. 9 times out of 10, when I'm driving myself insane coding, it's because I'm not obeying my own advice here. So this is also like a reiteration for my own benefit. Do these things, makes my life better. Okay, here's one bonus function I throw in just for fun to show you an application I use very often. So the lecture slides that you see for this class, they're actually rendered with a function. So this is a function here that I just give it a numeric week for the lecture. And what it does is it browses down my directories, finds the relevant RMD file for the lecture, knits it into the slides. It also creates a .r file for you to follow along in, and then it opens the slides in Chrome and prints them to a PDF. Okay? So every time my slides are knit, it does all of these things and runs them, and it gives me update messages as it's going. Functions are useful for this sort of repetitive operation. It allows me to regenerate my class instantaneously and update everything. It's kind of nice. It actually occurs to me I forgot to do this on the slides when I updated them yesterday, so the PDF is out of date. So I'm going to run that here in a second. Okay, so your homework for this week is to download and analyze data from the first year of Seattle's failed Pronto bike sharing program from some years ago. You have a template that's provided. You're going to write a loop or an lapply to read in the data from multiple files. I don't want you to just use Vroom. You can also if you'd like. You'll write functions to clean up the data, and then you'll write a function to visualize bike ridership over the first year. There's a little bit of string processing needed, which you've probably mostly seen in labs and homeworks, but I will cover it next lecture. And I give some suggestions in the template. I'll go over it in lab if need be. Part 1 is due next week, and then part 2 due the week after. And I will say right away, this data set is the opposite of the data set I gave you in the prior homework. The prior one is a hideous monstrosity. These are perfectly clean, pristine data that are well organized because they were generated by a machine. And so they're sort of nice, simple data. Whereas the administrative data is actual like vote tallies, which was made by humans who do not tend to tabulate data nicely. Okay. So that's all I got for you today. I'll see folks on Monday lab, and we'll go over the homework.
Thank you.
Thank you.
Yeah.
Do you have time for one quick question?
Yeah, absolutely. Let me print my slides really quick. I forgot I got to update that PDF. I'm listening though.
I missed something. What is the motivation? I understand what it did, but what is the motivation to do an anonymous function?
Well, if you're not going to use it, you don't need to. If you're not going to use it more than just there, you're never going to like reuse it. Why waste your global environment space with it? And the funny thing is we actually are using anonymous functions basically constantly. So for instance, if I just say like, So if I take my gapminder data and I say mutate pop mil equals, right? That's actually an anonymous function on the right side. I just haven't specified. In some languages, you would literally have to specify that as a function to use it. So we basically use them all the time. It's just that if you want to get something more complicated, maybe you want this to, like if I want to do this in an apply statement in some way, I would actually have to be able to pass the variable. And so it would kind of get annoying. So like the apply version of this would be to say, so you want to do it with pop mil.
So the idea is that it just clears the intermediate steps when you're done with them?
Yeah, so nothing gets saved because anything that occurs, so there technically here, there aren't really even any intermediate steps. It just lets you do this without saying, like pop mil equals function of X here where I in this case, what would I have to say? I'd have to say like, God, how would I even call on that anonymously? Yeah, it would be a heinous to make a non-anonymous version of that. It'd be better to do this with an lapply version. So the idea is it just lets you perform all the normal operations you'd want to do. Is kind of the thing. It's clear with something like lapplies. I mean, for instance, I want to say like gapminder here, give me the function mean x na.rm equals true here. If I want to just get all the numerics, let's see. Yeah, this is all heinous to do this stuff this way, but I do it. Oh yeah, no, I have to apply over.
So my confusion isn't why not name it. My confusion is why not just write it as plain code instead of doing function? What is adding the function?
Oh, like an lapply or something where you put function, not the code?
Yeah, like why are we introducing a function if it's just going to be for one line of code?
Well, some things they literally you have to say, like if you try and do that lapply without the function there, it actually doesn't work because it has to be created as a function to run it over all that. In dply, in like similarly in like mutate, when I say mutate like across here, if I have a bunch of vars here and I want to go over them like this, you actually also have to specify. So the tilde is essentially doing that for us and specifying it. You have to because it doesn't know what the hell to do with it if you don't do it. Mutate here, I can say like as dot numeric here and make this is still actually technically an anonymous function. I just don't have to write function X. But you have to, it's kind of the idea. So it just doesn't work.
When do you have to? When is it mandatory to use function X?
Literally anytime you're using an lapply, if you basically anytime you're doing, so here I'll show you. So if I say lapply Swiss, I could say mean here. This is not an anonymous function because I'm directly calling on the mean function.
Right.
But if I wanted to do na.rm equals true, well, I could actually say na.rm equals true, and it will add na.rm to this. But if I want to do mean divided by SD, right? Well, now it's like, I don't know what the hell you're trying to do, right? Because it doesn't evaluate mean and SD before it tries to do the division. But if I say here, still doesn't work. Object X not found because it doesn't know how to pass it. Gotcha. This says pass those arguments as the first argument of X, and then that makes them go to here, and that makes it calculated. So gotcha. The anonymous function is sort of, the function is necessary here because it tells lapply how to send this into the first argument of this, which then puts it here and here.
Gotcha.
In dplyr, you don't have to do it because technically the tilde and the periods is doing all that magic for us, but it's actually doing the same thing function X is here.
That seems important and complicated, and I'll take a while to get my head around it. Thank you.
That's normal. Yeah. Okay, next one. What if we need to use an unquoted variable outside of ggplot? It generally works in dplyr functions. So dplyr, it doesn't really care most of the time. Like I can do weird shit like, let's see. And it gives me both of them. God only knows why. So you can do stuff like that. It'll probably get weird. You probably won't like it in a mutate. Like this probably won't work. Yeah, no, non-numeric argument to binary operator. But oddly enough, I could do it over here. And that will work. Who knows why? And the reason is this allows you to, in a function or something, programmatically assign a variable. Yeah. Does that answer your question? Okay, question on slide 16. Yeah, what you got?
So this is probably pretty basic, but I guess I'm just still not, I'm confused as to how, if you only have quants in your return portion, how it also knows to return the names. Is it because you specified quants in names?
So yeah, I created the quants object here, and then I assigned names to it right here. And by assigning the names, when I return it, it spits it out with the names attached.
Okay, so you wouldn't have to write, because like names is kind of its own object. So you wouldn't have to write like return quants, comma, names.
So names are weird. So if you assign something, names are actually a meta property of an object. So they're what's called an attribute. So they are part of the object quants here, but the way you can assign things to them is by you're essentially selecting the names attribute of quants and then assigning something to it, but they're actually going into quants. They just happen to be going into its slot for attributes.
Okay.
Yeah, it's a little bit weird. Names are a part of the object. You just don't access them the way you would access other parts of the object because there's something called an attribute. Yeah.
Okay, thanks.
And attributes follow it when we do a return. Yeah. Anything else?
Thanks, Chuck.
Yeah.